So hash table is another kind of data structure. It helps to store data, but it's a bit different than the array. For the array, you're saving values in a contiguous manner in the memory. But in the hash table, it utilizes a hash function that can take the keys and then it converts into the indices. And for that, it helps to store in different parts of the memory. And searching become really fast for the hash function. For array, the searching is big of n, but for the hash table, the searching become big of 1. Database can utilize this kind of faster execution. But let's look at this example here for hash table. We have a key 10 and the size of the hash table is 5. So if you do the mod, it is stored in index 0. But for 15, if you do the same mod, it's trying to save at the same index position. And this is what is called collision, trying to save the value in the same index position. And there are different values to avoid the collision. We have the open addressing, solve it as you go, and then you have separate chaining utilizing linked list, and Robinhood hashing to switch off the keys. But for today's class, we're going to talk about linear probing. So what is linear probing? Linear probing actually a simple strategy to say, look at the next available slot. If you don't have this current slot available, look at the example. We have 0 to 10, 11 size of the hash table, and we have this position occupied. We have the key 26. The 26, the hash tables have 11. If you do the mod, we got 4. But the 4 has a collision, 5 has a collision, 6 has a collision, 7 is empty, and we can use that. So we can see the length of the hash table and available elements. These has a fundamental performance aspect in here, and we call it load factor alpha. And alpha is n by m. And we can see if higher the value of alpha, the more collision we have. So now the next part, what we're asking is, if we give you a known load factor alpha, can you tell us how many times you need to try in linear probing for a successful search? Okay, and you know alpha is n by m. So these values are here. So now what we do is, suppose we are trying to insert the ith key, like third or fourth key. At that moment, the table is full I by m. Very simple. Okay. So for that, what is the expected probing that we need to do? Whatever value is available to do that. This is the calculation for one single element. If you want to do for all the elements, the probing for all elements of the hash table, you do the average. You sum of the values, you divide the total. That is called average. But here we don't have anything to do with the load factor here. So now we're going to change this I by m, because we know xi equal to I by m. We change that. Why? Because it will change our range from 0 to n minus 1 to 0 to alpha. So now we got to do a discrete sum with the integration that has a load factor as a range, and we make some assumption. So we take that part, we utilize this part, take it. We know this is 1 by x, that is ln of x. You got it. Now you plug in these two ranges, right? You plug it alpha, you get this. You plug it 0, you get this. You end up this one. So take this, plug it in here. We have this value minus ln 1 minus alpha. So ln x, we can say 1 by x, as is negative, so we have that value. So ultimately, this is the successful probe that we can expect when we know a value of alpha. What is the usefulness here? We got the alpha, we plug it in. So when we have alpha value of 0.5, we know for a successful probing, we have the value of 1.39. And if you look at this graph, the x-axis talk about the load factor alpha. This is the expected successful probe we have. Until we have below 0.7, this is a good range. After that, we have degradation in performance. So keeping alpha below 0.7 is really important. But even though if we have higher alpha, we can increase the size of the table or imply different other techniques. So these are very gist of the whole load factor and the successful probing for the hash table. Thank you.